For topic 5, we're going to take polar equations and we're going to convert them to rectangular equations. And what you need to like really understand when you're dealing with rectangular, we need all x's and y's. For polar, we need r's and theta. Okay, so if you're taking something that is polar, you need to convert the r's and the thetas into like x's and y's. Okay, so this can be a little wacky. It's kind of cool though the way it all like translates. So again, these polar equations, they're gonna have like sines and cosines, they're gonna have r's and they're gonna have thetas. All of that needs to be converted to this XY world that we're so familiar and comfortable with. Okay, so we have a couple of things that we can do. Now, this is not always tried and true, but when graphing polar equations, it's sometimes easier to convert to rectangular equations and then graph. And the opposite is also true. There are going to be some situations where having an equation in rectangular form is going to be just bananas, so we convert it to polar form. Okay. Now, to do this, we have two helpful techniques. One thing we can do is we can multiply both sides of the equation by r, and some magical things can happen. And sometimes we can square both sides of the equation and magical things happen. Now, sometimes neither of those is going to be the most useful thing. So I do have one example where we're not going to square both sides. We're not going to multiply both sides by r. We're going to do something else, okay? But you'll see it when the time comes. Now, once we do that, we're looking for these common substitutions. We know that r squared is equal to x squared plus y squared. So if you see an r squared all by itself, convert it, x squared, y squared, okay? If you have an r times cosine theta, convert it, make it an x. If you have an r sine theta, convert it, make it a y. Also, we need to remember that tangent of theta is equal to y over x. So we have these like four things that I have kind of in these little braces. We have these four things that are common subs that we can do, common substitutions that we can do that help us convert from that polar format where the r's, the thetas, the trig functions and stuff are there into this world that we live in with x's and y's, or not that we live in, that we're more comfortable in. Okay, so let's go ahead and look. So example 6 here says convert each polar equation into rectangular form. That means we want x's and y's. Okay, so for the first example, we have r equals cosine theta. Now we're trying to find situations where we have these common substitutions. And remember, our common substitutions are we need to look to see if we can get an r squared because then we can convert it to x squared, y squared. We want to look to see if we can get an r times cosine theta because that's really just an x. Or if we can get an r times sine of theta, that's really just a y. And then we also have this tangent situation. Okay, so let's see what we can do here. Well, right off the bat, I think let's try multiplying both sides by r. Okay, so we're going to multiply both sides by r. And I'm going to expand this a little bit. I had it shrunk down so we had room to see something. I'm going to expand this a little bit, make it bigger again. Okay, so when I multiply both sides of the equation by r, on the left I'm going to get r times r, which is just r squared. And then on the right, I'm just going to get r times cosine theta. Well, I'll be daggum. How convenient is that? We multiplied both sides by r and look at what we got. We know that x is equal to r times cosine of theta. We also know that x squared plus y squared is equal to r squared. Well, we have both of those things right here. So let's just do the conversion. Let's do these substitutions. So we're going to change r squared to x squared plus y squared. We're going to change r times cosine of theta to just x. And then technically you could kind of stop there. A lot of times we'll do some more. So in this case, I'm going to set it equal to 0. I'm going to make it look kind of more like the equation of a circle. So we're going to subtract x from both sides. And I'm going to write this as x squared minus x plus y squared equals 0. Now you could stop here, sort of, but when we have this x squared situation and this y squared situation, it feels like a circle. So you have that standard form and general form of a circle. So we want to write this we want to write this where we have kind of like our x and our y as two separate pieces squared. So we can see where the center of this circle would be, okay? So this requires, y'all remember completing the square? Are you cringing? Okay, so we get x squared minus x. We want to leave a little space to actually complete the square. Our y squared is all by itself. We're just going to leave it alone. And then we get 0, but the thing is, when you complete the square, whatever you add to the left, you got to add to the right. Okay, now to complete the square, we take b over 2 and square it. So b being the coefficient of the single x in this case. So the coefficient of x is -1. So I want to take -1 divided by 2 and square it. Well, that gives me positive 1/4. So that's what I need to add to both sides. I get positive 1/4. Okay? Well, over here, the reason we do this is it gives us something that is a perfect square trinomial, which factors beautifully. Like we're talking chef's kiss, right? So what we can do is we can take the coefficient of x, or the coefficient, we can take the square root of x squared, which is just x. We can take the square root of 1/4, which is just 1/2. Okay, this sign right here, let me get my draw screen back up. This sign right here tells me what sign I need in this factored form. Okay, and then I just square the whole thing. Okay, so then I get plus y squared equals 1/4. So what we have is a circle centered at 1/2 comma 0 with a radius that is the square root of 1/4. So a radius of 1/2. So that's what we're dealing with there. Okay. So I would have been semi-content if you stopped here, but we're mathematicians, right? So like, let's just take it all the way. Okay. Now, for the next one, this is the weird one. Okay, so we have these two tricks, these two techniques that we can use to convert from some kind of polar equation to some kind of rectangular equation. We can square both sides of the equation, or we can multiply both sides of the equation by r. But sometimes you can do some other things. So let's rewrite this equation. I'm going to rewrite this as sine of theta. I'm going to erase that and I'm going to try to write it correctly. I'm going to write this as sine of theta over cosine theta times cosine theta, except I'm going to write that one correctly too. You can always tell how late it is by how stupid I get in these videos. It's real late, y'all. So cosine theta. Now, my reason for separating the cosine and not writing it as just cosine squared theta is this. So let's rewrite this as sine of theta over cosine theta because we like that. That looks like something that we can use times 1 over cosine of theta. Well, what is sine of theta divided by cosine of theta? That's just tangent, right? So we get tangent of theta times 1 over cosine of theta. Well, let's see if we can just get rid of this denominator. Let's multiply both sides by cosine theta. So let's do that in blue. So we're going to multiply both sides by cosine theta. And then we're just going to kind of like rearrange things and tweak them a little bit. Well, over here on the right-hand side, the cosine thetas, they just kind of divide out. That just becomes 1. Okay? So I'm left on the left with r cosine theta equals tangent theta. So let's see if that helps us. Let's go back up to those substitutions that we can use. So we know that if we have a tangent of theta, we can rewrite that as a y over x. We know that if we have an r cosine theta, we can write that as an x. So we have two substitutions that we can use right now. So we can say, okay, we're going to rewrite this as x. So this is x. This is y over x. So x equals y over x. Let's see if we can solve for y, because a lot of times when we have these rectangular equations, their y equals something. So in order to solve for y, we would multiply both sides of the equation by x. Well, these x's just divide out, so I'm left with y equals x squared. So that's kind of cool, right? So just by sort of thinking, hey, could I separate this cosine squared theta? Sure, let's separate it. Well, then we have a sine theta over cosine theta, which we know looks like tangent. And then we have this like leftover denominator of 1 over cosine theta. So let's see what we can do with that. Let's just multiply both sides by cosine theta. And bam, it was like magic. We got that r cosine theta on the left. We got the tangent theta on the right. We have two substitutions for that. At the end of the day, we get y equals x squared. Okay? So let's look at C. Now, in the first example, we multiplied both sides by R. In this example for part C, let's square both sides. My reason for squaring both sides instead of multiplying both sides by R is if I multiplied both sides by R, I would get that R squared on the left, which would be great. But then on the right, I would get 5R, and then I would just have this extra R that I don't know what to do with. So let's square both sides here. So when we square R, we just get R squared. When we square 5, we get 25. And remember, R squared equals X squared plus Y squared. So let's replace our R squared with X squared plus Y squared. And that looks, hopefully, it looks really familiar to you all. This is a circle centered at the origin with a radius of 5. And that kind of should sort of make sense. Okay, we have R equals 5. Okay, what does that mean? It means we have some distance of 5 from the pole, but we don't really have any angle. We don't have like a specified angle. So we're basically saying for any old angle on the planet, any angle, we're going to have some distance of R from the pole. So that creates a circle centered at the origin or centered at the pole that has a radius of 5. Okay. Now, for our last example, let's do that whole multiply both sides by R because I'll get an R squared for sure, but then I'll get something with R sine theta, and we know R sine theta is one of our substitutions. So let's multiply both sides by R. So when I do that, I get R squared equals 4R sine theta. Okay, so we get 4R sine theta, and then that equals R squared. So we have two substitutions. Remember, R squared equals X squared plus Y squared, and we know that Y is equal to R sine theta. So let's do those two substitutions. So we have X squared plus Y squared equals 4 times just Y. Okay, well, this very much feels like a circle, so let's see what we can do with this. Let's start by setting it equal to 0. In order to set this equal to 0, we need to subtract 4y, okay? And then just like we did in part A, let's see if we can write this in like that standard form for a circle. So I'm just gonna leave my x squared alone. There's no other x, I don't have to worry about it. So I'm just gonna leave x squared. But then my y squared, I wanna see if I can do that completing the square to get some factored term where I just have the 1y. So I've got y squared minus 4y. We need to complete the square, so that means we're going to add something to this y squared minus 4y. But if I add something on the left, I have to add something on the right as well. So let's make a space for that. Now, to complete the square, we want to take b, divide it by 2, and then square it, where b is the coefficient of just plain old y. Okay, so we're going to get negative 4 divided by 2 squared. Well, that's negative 2 squared, which is just 4. So we want to add 4 to both sides of the equation. And now this right here, this stuff that's all in y, this is a perfect square trinomial. That is like literally the point of completing the square. You're forcing something to be a perfect square trinomial, and we like perfect square trinomials because of the way they factor, okay? So what we end up with is x squared plus, now this is going to factor as some binomial squared. So we want to take the square root of y squared, that's just y. We want to take the square root of 4, it's just 2. And then this sign right here is going to be the sign in my factored form. So this needs to be a minus as well. And then that equals 4. So what we now have is a circle centered at 0, 2 with a radius of 2. Okay, so not bad, right? I mean, it takes a little bit. You got to remember your circles. So you got to go way back to goodness. When was that? Like chapter 2 or something in your Math 171 course? You got to go back to that idea of circles, and then you got to remember completing the square, which is a little bit, it's a little much, okay? But if you can remember circles and if you can remember completing the square, look at what we've got. This is fantastic. We were able to take these 4 gnarly looking equations and convert them to stuff that we're really quite familiar with. This right here for part A, that's just a circle. Part B is just a parabola. Part C and D are really just circles. So we took these weird unknown polar equations and we converted converted them to something that's familiar to us, okay? Now that's it for this video. In the very last video, we're going to take rectangular equations and convert them to polar, and these don't work as pretty. Well, they're not too bad. All right, so I'll see you in the next video.